Now that we have a method to find critical points, we would like to figure out how to classify those critical points. Are they going to be local minimums, maximums, or possibly neither? So we're going to start with some examples. In each of these examples, 0, 0 is going to be a critical point of the function. And I've graphed each of the functions so that we can understand what type of critical point 0, 0 is in each situation. So I'm going to start with the example z equals x squared plus y squared. Okay, the gradient of z is equal to 2x, 2y. And so that means that if I plug in the point 0, 0, I get the 0, 0 vector. That tells me that 0, 0 is a critical point. So you can look at the point 0, 0. That's at the bottom of this paraboloid, this bowl shape. Okay, and so clearly 0, 0 is a local minimum. In this case, for this function, it's also the global minimum, but we're going to worry right now about classifying local maximums and minimums. Now I'm going to move on to the function 4 minus x squared minus y squared. Okay, in this case, the gradient of z is very similar. It's going to be negative 2x, negative 2y. And so if I plug in the point 0, 0, I again get that the gradient is equal to the 0 vector. And so 0, 0 is a critical point. But here, when I look at 0, 0, okay, that's going to give me z equals 4. That's going to be at the top of this paraboloid, this bowl shape. Okay, that is going to be a local maximum. Okay, now let's finally look at the function z equals y squared minus x squared. And so here we have the gradient of z. The gradient of z is going to be negative 2x and 2y. And so the gradient of z at 0, 0 is again going to be the 0, 0 vector. And so 0, 0 is a critical point. But now when I look at the point 0, 0, right there, it's a little bit tougher to see whether that's going to be a maximum or a minimum. Okay, so if I look at this from a side view, it appears that when I'm looking at traces that we've got points that are going down like this from the critical points. So at this perspective, it looks like it's going to be a local maximum. But if I kind of turn the surface, then we've got that it's actually not at the top of some mountain, but it's also, it seems to be at the bottom of some valley like this. So when I look at these traces, it seems to be at the bottom of a parabola. Okay, and so for this surface, it seems to, if I look in that direction, it seems to be a local minimum. So it depends on the perspective that I'm looking at this function, whether it looks more like a local minimum or local maximum. Okay, so in fact, this is going to be neither. So this is going to be neither, but in this case, we're going to give some sort of name to this. So if you look at this shape, okay, there are a couple different items that you could use to describe this shape. If you're into horses, you might consider that to be a saddle point. Okay, that looks like, that shape looks like a saddle that you could put on a horse. Okay, so it is a saddle. Okay, but in recent years, I've had a lot of students who refer to that as maybe a Pringle. It looks like a Pringle chip. And so sometimes people want to call that a Pringle point. Okay. What's important, though, is that we have a critical point where the gradient is 0 for each of these functions. Okay, but we could have a local minimum, a local maximum, or neither. If we drew tangent planes, in each case, the tangent plane at the critical point is going to be horizontal. Okay, so a tangent plane down here, okay, that's going to be a tangent plane there at the bottom. Here we can have a tangent plane at the top of this paraboloid. Okay, and then we could even draw a tangent plane for that critical point on the saddle, and it would also be horizontal. So now I'm going to give you a method for classifying critical points, and I'm going to try to give you a little bit of an understanding of why this method works, but I won't be able to give you all of the details. Okay, some of the details that are involved require you to know a little bit more about linear algebra, and so you'll need to take kind of a future course in mathematics to get all of the details. But I'm going to try to give you a few of the details to help you understand why this method will help you with classifying critical points. Okay, so what we're going to look at when we're classifying critical points is we're going to look at something called the Hessian Matrix. And it's a matrix of second partial derivatives. So you'll recall that in single variable calculus that you used to use the second derivative test to classify critical points. And so this is going to be a multivariable second derivative test. Okay? So the Hessian matrix is a matrix whose first component is the second derivative of f with respect to x. The next component is the mixed partial, the derivative of f with respect to x, then y. Then the other mixed partial, the derivative of f with respect to y, then x. Of course, the mixed partials are going to be equal if we have a function that has continuous second partial derivatives. And then the final component is the second derivative of f with respect to y. And so now with this Hessian matrix, we're going to define the second derivative test. So we're going to suppose that f does have those continuous second partial derivatives. That way the mixed partials are going to be equal. And we're also going to suppose that the gradient at some point x0, y0 is 0. Okay, so we're going to look at critical points. So then we're going to define something we're going to call d of x0, y0. D of x0, y0 is going to be the determinant of the Hessian matrix. So determinants are something that we have seen before. We used determinants to evaluate cross products. So this is going to be the determinant of a 2 by 2 matrix. So if we think about what is the determinant of a 2 by 2 matrix, okay, you're going to multiply fxx and fyy, those pure second partial derivatives. Okay, we're going to multiply those two together. Okay, evaluating them at x0 and y0. And then we're going to subtract the product of the mixed partials, which is why I've written f sub xy squared. Okay, so we're going to look at this, we're going to look at the determinant of this Hessian matrix, and we're going to refer to that determinant as d, which is a function of x and y. In this case, we're going to plug in x0 and y0 because that's where our gradient is going to be 0. Now, d helps split us into two cases. Okay, the first case is when d is bigger than 0. So if that determinant is bigger than 0, then I'm going to get a local minimum or a local maximum. And then the second case is going to be when the d is negative. If the determinant is negative, that's where I'm going to get those saddle points. I'm not going to get a local maximum or minimum. So the first step is just, is that determinant positive or negative? If it's negative, no maximum or minimum. If it's positive, then we move forward. Now, if it's positive and this upper corner here, so we're going to look at this upper corner, if that is also positive, okay, we think about that as being a situation where the second derivative is positive, and we're going to get that concave up function. And you remember that when you have a concave up function, okay, and you have a critical point that's sitting at the bottom of that concave up function, that's going to be a minimum. Okay, so we're going to get a minimum. X0, Y0 is going to be a local minimum when that upper left corner f sub xx is positive. You can actually do the same thing with the second derivative with respect to y. You just have to pick one and then stick with it. So here we're just going to use the upper left corner f sub xx. Now, if that f sub xx is negative, what that's going to do is that's going to tell us that we've kind of got this concave down shape. Okay, we got an upside down bowl. Okay, and you'll recall from single variable calculus, if you have a concave down shape and then you've got a critical point that's at the top of it, okay, that's going to be a local max. And that really tells us the second derivative test. So we need to find the determinant of this Hessian matrix, and then we need to look at the sign of that top left corner, the second derivative with respect to x. Okay. Well, let's justify this just a little bit. Where does the idea come from? And the idea comes from a Taylor series. Okay, I know that's everyone's favorite topic from Calculus 2, the Taylor series. Okay, but there's a such thing as a multivariable Taylor series. I'm not going to ask you to calculate these things, but I just want you to make you aware of it. Okay, so when you're using a Taylor series, okay, we can say that f of xy is equal to f of x0, y0, and then plus, and then we would have the derivative. We would have the derivative of f at x0, y0, and then we're going to multiply by x minus x0. But in this case, the derivative is going to be the gradient. Okay, so we have the gradient, and instead of multiplying, we're going to take a dot product. We're going to take a dot product with x minus x0, y minus y0. Okay. In fact, if you look at this, this is the equation of the tangent plane. Okay. These first couple terms to this are actually the equation of the tangent plane. Okay. That's the first part of our series. Just like the equation of the tangent line was the first part of our Taylor series in single variable calculus. Okay. So after that, we need to have a squared term. And so this squared term looks kind of interesting. It's going to be x minus x0, y minus y0, dotted with the Hessian matrix of f at x0, y0, and then that's multiplied by another vector, x minus x0, y minus y0. So you need to know a little bit about matrix multiplication to see why that works. Okay, but that is the next term in the series. Okay, so you're just going to have to take my word for it that's the next term in the series. Okay, so we have a second derivative term there, and then we're going to have terms with third derivatives, but those are just higher order terms. So we know that a function, if it's has enough derivatives, okay, it's going to be equal to its Taylor series. So I'm just rewriting this function as equal to its Taylor series. Okay. Well, now that we have that term, okay, let's look at the series and notice that the gradient of f, well, the gradient of f in that case is going to be 0, okay, because we're going to be looking at this when we have a critical point. So this is going to be 0, and that's because x0, y0 is a critical point. Okay, so that part of it's 0. So what's kind of left? What's left is we have just the point x0, y0, and then plus, and essentially we have a function here. This whole expression that you see here, this whole expression is basically a function of x0, x minus x0 and y minus y0. So we're going to have a term that depends on x0 and y0, and then it's going to be multiplied by an x minus x0 squared and a y minus y0 squared. So if I simplify it out, it's going to have a term that looks like that. Okay, and then of course there's some more higher order stuff, but we can at least write it like that. Okay, and in fact, if we use Taylor's theorem, we can still write it exactly like that. This will be like the remainder term in Taylor's theorem. Okay, so we have something that looks like this, and then the sign of m depends on the criteria in the second derivative test. So that sign of that thing, m, it really depends on whether the determinant is positive, okay, and it depends on whether f(x) is positive or negative, okay? It's going to depend on that. And so what we have is that f of xy is equal to f of x0, y0, okay? And then we're either going to add something, okay, which is m times something positive. Missed a square there. Okay, so we're either going to have f of x0, y0, where we're going to add something, okay, in which case we have a minimum, or we're going to have f of x0, y0, where we're going to subtract something, okay, and then we're going to have that maximum, okay, or there's a possibility that it ends up being neither. It's neither always positive or always negative, okay, maybe it's sometimes positive and sometimes negative. So here m is just a term that depends on that criteria from the second derivative test, okay? And that's going to tell us whether f of x0, y0 is sitting at the bottom because m is positive, or it's sitting at the top because m is negative, or possibly neither, okay? So this all comes from the idea of Taylor series. And that's essentially the best that I can do for now. Hopefully this is a topic that you can revisit again once you take a little bit of linear algebra, and you can then clarify this test. But for now, you'll have to just take my word for it. Okay? So we're going to use this second derivative test. Okay? And we're going to use it to find and classify all critical points of the function f of xy equals natural log of x squared plus y squared plus 1. Okay, so to find the critical points, we're going to find the partial derivatives. So the partial derivative with respect to x is going to be 1 over x squared plus y squared plus 1. And then I want to take the derivative of the inside of the log. So the derivative of the inside of the log is just 2x. I'm going to set that equal to 0. The denominator is never 0. And the numerator is only 0 when x is 0. So that tells me x has to be 0 to have a critical point. I'm going to look at the y derivative. Okay, again, it's 1 over x squared plus y squared plus 1. The derivative of the inside of the log is going to be 2y. I'm going to set that equal to 0. Again, the denominator, I don't have to worry about it. It's never going to be 0. Okay, but the numerator can be 0 when y is equal to 0. So I get my first critical point. 0, 0 is, actually, it's the only critical point. Okay. Now, the next thing that I need to do is I need to find that Hessian matrix. Okay, so I want to classify the critical point. I need to find the Hessian matrix. So I'm going to take the x derivative of the x derivative. Okay, you can see that I have a quotient, so I'm going to use the quotient rule. Okay, the derivative of the top is 2. The bottom is x squared plus y squared plus 1. Okay, and then minus, I'm going to get 2x times the derivative of the bottom, which is also 2x. And divide the whole thing by the denominator squared. Okay, so that's my first term. Now I'm going to take the derivative of the x derivative with respect to y. Okay, so now the derivative of the top, I'm going to use the quotient rule again just to make things easier. So the derivative of the top is 0, and then subtract 2x times the derivative of the bottom, which is 2y. And again, the denominator is the same. It's x squared plus y squared plus 1 squared. Looking at the second derivative of the y derivative, so the derivative of the y derivative with respect to x. So I'm going to look at the derivative of 2y with respect to x and get 0, using that quotient rule again, minus 2y times the derivative of the bottom there, which is 2x. Okay, the derivative of x squared plus y squared plus 1 is 2x. Again, the denominator is squared. It's kind of nice. And then finally, the y derivative of the y derivative, okay, that's going to be the derivative of 2y, which is 2, times x squared plus y squared plus 1, minus 2y, which is the numerator, and then the derivative of the denominator, again, with respect to y, is 2y. Okay, and divide that by x squared plus y squared plus 1 squared. And so now I have the components of my Hessian matrix. Okay, notice I didn't simplify them. I didn't bother simplifying these because I knew I was going to be plugging in 0, 0. So there was really no point in simplifying. I might as well just plug in zeros and then see what numbers that I get. Okay, so here we have the Hessian matrix. Okay, we're going to plug in 0, 0. Okay, so if I look at f sub x, x, if I plug in zeros, I'm going to get 2 minus 0 over 1. So I'm just going to get 2. Looking at f sub xy, notice when I plug in zeros to the numerator, I'm just going to get 0. So that's kind of nice. F sub yx, okay, so the other mixed partial, I plug in zeros to the numerator. Okay, notice I get 0 again. Those mixed partials are equal, not just at 0, 0, but everywhere. You can note that these two are in fact equal. And then when I substitute 0 in for the second derivative of f with respect to y, notice again I get 2 minus 0 over 1. Okay, so it's just the matrix 2, 0, 0, 2. That tells me that D, which is the determinant of my Hessian matrix, okay, that's going to be 2 times 2, which is 4, minus 0. Okay, so an easy determinant there. Just multiply 2 times 2. Okay, so I get that D is 4. The second derivative with respect to x, okay, at 0, 0 is in fact going to be 2. And that's going to give me a local minimum. Okay, so if D is positive, I have a minimum or a maximum. And then the fact that the second derivative with respect to x is 2, that tells us, which is positive, that tells us that we have a local minimum. Okay, and I encourage you to graph this function, in fact, and you'll see that 0, 0 is a local minimum. If you were to graph this function, okay, you're going to get some sort of upside down bowl shape like this, in which 0, 0 is a minimum. Okay, right there. So 0, 0, 0 there is a minimum.